program was not happy. All right, so yeah, don't need that. What I do need is this. All right, so this is what I had on at the beginning of class today. But how this one is about change and rates of change. How I measure change, what I know if I know a rate of change, how do I use it, or how do I figure it out? So like I said, if I know how much of something I have, how do I determine at what rate it's changing at all points in time, or vice versa. If I know how fast something's changing all the time, how do I measure how much of it I have as a result? And it doesn't have to be actually time and an amount of something. It could be other sorts of quantities, but just thinking of like driving and speeds or temperature rising, something like that is maybe an easy way to think about what those two might mean. So just as a silly example, but one to introduce some notation here. Suppose that your phone states that your current programs are taking up 7.8 gigabytes of space and you download a new app that uses 0.5 gigabytes. We want to know how much space is now used by the programs. Not a challenging mathematical question, I hope. But suppose that symbol-wise we let Z represent the amount of space in gigabytes that's taken up by programs. So let's use these three in this. Z with a subscript I, I'll just call it Zi, being the initial value of Z. Z with a subscript of F, I'll call it ZF, as a final value of Z, and DZ to be a change in Z's value. So these might seem familiar from like final minus initial, something like that. Y final, Y initial, if you're calculating slopes, or Y2 minus Y1, that sort of thing. But what I want to talk about this DZ. So if Z is representing an amount of something, DZ, this symbol we're going to use repeatedly in this class to represent an amount of change in the quantity Z in this case. So a D in front of another letter we're going to use to represent a change in the quantity that that other letter is representing. So thinking about these three symbols, in terms of this situation here, what is the value of Zi, the initial value of Z in this situation? Yeah, 7.8. Initially, your applications were taking up 7.8 gigabytes of space on your phone. All right, so what about ZF, the final value of Z? Yeah, that's the one we have to figure out. 8.3, it's like after you add additional programs, download an extra one. That's that ZF, the final value of Z, the amount of space taken up by programs after something's happened. And so what's the value of DZ? Yeah, it's 0.5. Now, something else to think about with DZ, it's talking about a change. Changes can be a change that makes something increase or a change that makes something decrease. In this case, it's an increase, and so we call that a positive 0.5. Just like usually, you don't have to specify positive. If you just say DZ's value is 0.5, 0.5 is a positive number. But keep that in mind when you're talking about decreases. It's very easy to forget the negative sign if you're just thinking about the size of the change as opposed to the direction of the change. If you're dealing with a lot of increases, you just keep saying this size of the change, and it's the same thing, thinking like absolute value or the amount of difference. But we actually want to know the direction of difference. So this is 0.5, but if you want to clarify that you're actually talking about a change, you can maybe even say it's a positive 0.5, indicating a positive or an increase in value of Z here. Z are amount of space consumed by a program. So using the same notation, let's see, here we go. Second situation. So think about those same things. We're going to use Z here as an amount of memory or space, different in different examples here. But whatever this might be, at first, opening up my device, maybe it's a laptop, 3 gigabytes of memory is being used. After starting a new program, 5.5 gigabytes were being used. Think about, of those three quantities we were talking about last time, initial, final, and change, Zi, ZF, and DZ. If we let Z, in general, represent the amount of, in this case, memory that's being used, think about what are the values of each of those other three. One you'll have to figure out, and the other two are given. And then I want to talk about how these are related to one another. So which is there's two numbers given. Which symbol represents the quantity of these three here that isn't given, ZI, ZF, or DZ? DZ. It doesn't state the change, but we can compute it by doing what computation? Subtraction. All right, so to subtract what specifically in symbols, what would I be subtracting to find the value of DZ? Yeah, ZF minus ZI, Z final minus Z initial, or the final amount of memory minus the initial. By doing it that way, if I get a positive quantity, that means the final was larger than the initial. If I get a negative quantity, that would mean that the final was smaller than the initial. That sounds right, because going forward in time from initial to final, if it's shrinking in size, I want to indicate a negative change. So when we do that subtraction, we're going to do final minus initial to get the sign, the positive or negative, to come out the way that we want it. All right, so DZ here and everywhere then is going to be Z final minus Z initial. So I could write that in general, or for this one, if I wanted to do the computation, if I want to say DZ, it would be number-wise 5.5 minus 3. So what, 2.5? That's not a hard math question, but somehow my mind's escaping me now, right? 2.5 gigabytes of memory was being used, the change due to opening this new program. So think about the same things with this. When you get your computer, 14 gigabytes of disk space was being consumed by your operating system. You've added programs and files that take up an additional 40 gigabytes of disk space. Think about relative to Z, meaning an amount of memory or space used. What are these two numbers values of? And determine the value of the unmentioned quantity. Let's see, so which quantities, which symbol are we missing? ZI, ZF, or DZ? I hear a couple different things there. Let's see, so 14 gigabytes of disk space was being used when you got your computer. That sounds like a value of ZI, initial value. What is this? You've added programs that take up an additional 40 gigabytes of disk space. That's a value of DZ. So the part that's missing is the ZF, all right, the final value. If I wanted to find the final value, the amount of disk space that now at the end is being used by your programs and operating system combined, what would I do with these numbers here? Add, right? So Z initial plus DZ equals ZF. It's the same expression, just rearranged from what we had before. Z final minus Z initial equals DZ. That's what we said for the first example, but just algebra rearrangement. This is just adding and subtracting things. If I have an initial value ZI and I add on some amount of change, I will have then, Z's final value, the value after the change. So these are just the same expression rearranged in two different ways. And these are two of the most common orders in which we'll see things. Obviously, we could also have what ZI isolated. I could say ZI is equal to the final value of Z minus a change, if you need to work backwards and see what happened at the beginning. Or take a look at this. Your phone was filled with apps which are taking up 23 gigabytes of memory. You deleted 5.7 gigabytes of unnecessary apps. Deleted sounds like subtraction. Is it this? No, it's not. There's subtraction, but only because, let's see, you deleted 5.7 gigabytes of So you've decreased the value of z. You've decreased the amount of space being used. So that's just a change. That's a dz that happens to be negative, right? So it's really this. Your phone was filled with apps. Initially, you had 23 gigabytes of space being taken up by apps on your phone. You deleted some. You added a negative 5.7 gigabytes. And what's missing here is actually the final value of z. So there is something that's subtraction-ish about this. When you read it, it's like, oh, I just subtract that, I can figure out what's left. But that doesn't necessarily mean that what I found by doing this subtraction is this. You can't just say, oh, there's subtraction, so therefore. Make sure when you're reading a problem, you think about what the quantities are representing. And keep in mind these negative changes. I wrote this as plus a change, but your change could be could have a positive or a negative value here. Initial value plus your change could be initial value plus a negative number, which it is in this case. And if you want to subtract this, feel free. Let's see, 17.3, maybe if you subtract this. Okay. Not the point of this to do practice with subtraction, but that said, make sure you can subtract when needed. So a change in a quantity is computed by finding final minus initial. You can find dz, or whatever the letter is, by doing zf minus zi. And again, I just picked z for fun, because why not? If it was x we're talking about, I call it x final and x initial, xf and xi. Doesn't really matter what the symbol is that I'm using to represent this quantity, but it's a symbol that's representing some quantity that apparently is changing. So when I'm representing, and this we'll talk about this more next time, but if I'm trying to represent a quantity that's changing with a symbol, the symbol that I use is called a variable because it varies in value. Things that don't vary in value, but we're using symbols for them, are not variables. They could be something else, a parameter, a constant, something. But variables is then actually the name of something that the term is used incorrectly a lot. Anything that's a letter is called a variable sometimes. Not always. A variable has to be, based on its name, it's something that's used to represent a quantity that's changing. So, in any case, if I'm talking about a change or a variation in a value of x, mystery thing, whatever this quantity is, we'll call it dx. We can do final minus initial. Also, getting into what we were talking about earlier with time and temperature and that sort of thing, or driving and distance at various speeds. But if I have a second quantity, a different letter, so last time we just talked about z, just the gigabytes of space on your phone, or your gigabytes of phone memory being used, or space on your operating system disk, whatever it was. Those are just one thing at a time. If I'm trying to relate two things, if y is changing along with x, if one thing causes a second to change, or if both things change in conjunction with one another, regardless if one causes the other or they both just happen to change, we can find how much one changes because of the other if we know enough about them. So instead of talking about just like, oh, changes in x, x initial, x final, dx. If I know that x is related to y, if I know how much x changes, and I know something about their relationship, I should be able to figure out how much y changes also. Whether it's just knowing a function that relates y to x, or maybe I know something about the rate of change between y and x. The rate of change of y with respect to x is usually the way that the letters go. But you can determine amount of change in one from the other's amount of change if you've got related quantities. So this is called a rate of change. So a rate involves two different quantities being compared. Maybe it's miles per hour, maybe it's people per square foot, maybe it's dollars per day, lots of different sorts of rates, but they always involve two different quantities and how when I change one, the other changes. And whether they cause one another to change or they just kind of both will be changing depends on the situation. But we'll call that a rate of change, the change relationship between the two of them. So let's talk about constant rate of change, which I mentioned this word earlier when we were talking about looking at a small section of a parabola. Looks like it had a constant rate of change. Visually, constant rate of change is related to slope and straight lines. So let's think about this in terms of a story, though, instead of just a picture. Suppose you're driving in your car, and once you get on the highway, your car's cruise control is set to travel at a constant 70 miles an hour. You hope you don't run into traffic, but if you're kind of a empty highway, you can probably do that for at least a little while. So this 70 miles per hour is a constant rate at which we're traveling. Think about, what does that mean? Well, every extra hour that you travel would mean that you travel an additional 70 miles, right? So that's one thing we can say. This is certainly a true statement, but this doesn't say everything that 70 miles per hour says. Because, well, for instance, you don't have to travel a whole hour in order for 70 miles an hour to be calculated, correct? Right? Like, so police tell you you're going 70 miles an hour, they pull you over, you're going 70 and a 35. Like, but I have only been driving for 5 minutes. That's not a good excuse. Like, you don't have to go a whole hour before there's a speed that goes with it. So it doesn't have to be just a whole additional hour. We can expand this to talk about the relationship between time and distance in general for any amount of time traveled. So because it, like, every hour means 70 miles traveled, means in 2 hours I'd go an extra 140 miles, but 5 hours, I could talk about half an hour, right? Things that are smaller, I don't have to go just multiple whole numbers of hours. In half an hour, you drive 35 miles, right? What about in a tenth of an hour? 7 miles. Well, how could you calculate, like, let's say I said, well, I want to know how far you go in 1/1,000,000th of an hour. There should be a way to do that, right? Any thoughts on what you do? If I said, how far would you travel in 1/1,000,000th of an hour? Yeah, you multiply 1/1,000,000th and 70, right? So if it's 2 hours, I do 2 times 70. If it's 5 hours, 5 times 70. Half an hour, half times 70, or half of 70. Tenth of an hour, 1/10 times 70. A millionth of an hour, a millionth. Whatever the number of hours is, whether it's a nice number or not so nice of an hour. If it's 0.0073809 hours, if I want to know how far I traveled, if I'm traveling at 70 miles an hour, multiply. Whatever the amount of time is, the number of miles is 70 times that number of hours that have gone by. So during a little incremental change in time, for any change in time, so if I let a little bit of time go by, X is representing time here in my notation. If I multiply it by 70, I'm going to get the amount of distance that I covered during that small amount of time. So if I let X represent, I haven't defined my variables here, but if I let X represent the amount of time since you started driving, and Y equals the amount of distance since you started driving that you've covered, where X is measured in hours and Y is measured in miles. Those would both be things that if you're driving, those are changing. And you're driving at 70 miles an hour, if I let a little bit of time go by, whether it's from the start or during any little increment of time during the drive, take that amount of time times 70, and I'll get the amount of distance traveled as long as I'm using my units properly, as long as I'm measuring the amount of time in hours. Multiplying by 70 will give me the amount of distance during that time in miles. So this is the same concept as what here, you're going 70 miles an hour, in an hour you go 70 miles, and you can scale it up. You can also scale it down, or talk about in general what I do with an amount of time that passes in order to get the number of miles that occurred because of that time passing. The number of miles driven because some time went by, while I was driving at this constant speed. So I know this seems kind of like, this is getting a little intense about driving 70 miles an hour, but the premise is that, well, in this case, we have this constant rate. I can use that to figure out what happens, regardless of whether this amount of time that goes by is a large number or a small number or anything in between, medium-sized number. This is how that rate of change functions for us. It relates the two quantities in this multiplicative way. The amount of change in one variable's value and the amount of change in the others are off by this factor of 70, a multiple of 70. So here this is in words. For any additional time traveled in hours, the distance increases by 70 times as much. We're just measuring that distance in miles. And it says increases by 70 times, because notice this is a positive rate of change, a positive velocity. So I will have gone 70 times whatever time it is in a positive direction or farther, as opposed to like going backwards into some black hole. So let's think about something that doesn't involve time and distance. You're filling up your gas tank and the gas costs $2 per gallon. Whether or not you really think of it this way, that is a rate. It's a rate of change if I'm changing what I'm purchasing here. So if I buy more gas, it costs me more money, right? Like, it'd be nice if gas were $2 a gallon. It's not. But if I buy, according to this, if I bought 1 gallon of gas, it'd be $2, or 2 would be $4, 10 gallons would be $20. But it doesn't matter. You don't have to buy whole numbers of gallons at a time. It often comes out to weird decimal numbers of gallons, and any incremental increase in the number of gallons of gas you purchase, usually it only goes up because you can't take the gas back out of the gas tank, is going to cost you $2 times that extra number of gallons more than it would have before that. So you can say that every gallon that you purchase means $2 more in cost, but you don't have to go up by whole numbers at a time. So this isn't wrong, that's not what I'm crossing out, but just like if you want to explain what this rate means, that's one example of what it means. But what it really means is that in any situation, just any number of additional gallons of gas purchased times 2 is going to give you the cost of that extra gas that you purchased, where the cost is measured in dollars. So as long as I'm using my units properly, and any additional number of gallons of gas purchased times 2 gives me the extra cost in dollars in this situation. So it's not just an extra gallon costs $2. That's a good place to start, but you can build on that and use it in any size of change situation, not just incremental whole numbers at a time. So in general, this constant rate of change idea, if I have y and x, generally speaking, not a specific story, but if I have y and x in a constant rate of change relationship, this statement is going to be true. dy equals m dx, where I'm using this m as the multiple that we were talking about. The 70 when we were talking about 70 miles an hour, the 2 when we were talking about $2 per gallon. That m for multiple maybe looks familiar. Y equals mx plus b. It's the same m, but notice this isn't that equation. This is telling us something that's related to that, but it's talking about a different aspect of it. So y equals mx plus b tells us if you know a value of x, how do you calculate the value of y? This statement here is relating changes in the value of x to changes in the value of y. And if they're in a constant rate of change relationship, meaning if you want to think about y equals mx plus b, if you're talking about stuff that exists on a straight line, points that are somehow graphed and they end up straight one way or another, if you change the x value from any one point to any other point, multiply it by this m, the slope, you're going to get the corresponding amount of change in y. So if you want to relate it to lines and linear equations, that's fine, but realize that this is not talking about x values and y values. This is talking about amounts of change in x and y, or picture-wise, if I change x a little bit, y is going to change by a certain amount. If I change x by more, y is going to change by more. Because it's the same m, this change in my x variable and the change in my y variable that corresponds to it are in a certain ratio to one another. You've done like rise over run, that sort of thing. dy divided by dx, if you look at that expression there, is going to be equal to m. And it doesn't matter how big dy and dx are. If I make one bigger, the other is going to get bigger. Now this could be pointing down, and I could have a negative number that's getting more and more negative. But if I picked a different length of dx and dy, it doesn't have to be 1 unit long. Lots of times when you learn about graphing straight lines, because it's easy to graph them this way, it's like, oh, the slope is 3, so I go over 1, up 3, over 1, up 3, over 1, up 3. But you could also go over 1.5 and up 3 times 1.5. You can increase each variable by whatever amount you want, and the second will increase by the same multiple every time. So this, whatever the slope is, whatever that multiple is, the 70 miles an hour, the $2 per gallon, that number stays the same. If you change how much you're increasing or decreasing your x variable by, then the y variable will change, final minus initial, by the same multiple every time. So in terms of this picture I had over here, thinking about going from on a line from this point to that point, if I were thinking about x and y, wherever the axes might be, this would be maybe my x initial, y initial point at the left, and x final, y final at the right. That change is final minus initial, like we were talking about earlier. Like all these concepts are things that I know you've seen them before, but maybe didn't think about putting together just strictly this relationship here. Rearranged, like I said, I could have dy over dx equals m. That's the same as that y2 minus y1 over x2 minus x1. That's the same thing. That's telling you about how the changes in one variable are related to the changes in the other variable, or the changes in one quantity, whatever this variable is measuring values of, are related to changes in a second quantity. So just this notation here, keep in mind, this is just a rearranged version of something you've seen for years and years, but get familiar with this look to it. It's going to be very helpful for us, both in calculating this rate of change, dealing with using rate of change, and also we can use this if we have some initial values to find actual values of x and y that correspond. But just realize that this relationship here isn't talking about how values of x are related to values of y, just how changes in x are related to changes in y. So let's look at this example that is about snack mix gifts. So go put some stuff together, put it in a gift box, take it to a party, whatever you're going to do with this. So mixed nuts or candy and whatever you're going to put in there. So the box itself, let's say it costs $B. B here is not a variable. B is representing some mystery number I just don't happen to know. So the name of something like that is a parameter. It's a symbol that stands for something that isn't changing. It could be one number, it could be another, but the cost of this particular box is just some number that I didn't happen to list. We'll just call it B to call it something. So snack mix costs $2.75 per pound, which means that's a rate statement, $2.75 per pound, which means if I were to increase the weight of the snack mix that I buy, the cost is going to increase by 2.75 times as much, right? Any additional number of pounds of snack mix I decide to get, take an extra scoop, ooh, I got an extra quarter pound. Oh, well, that's going to cost me an extra 0.25 times $2.75, as opposed to what it would have if I'd taken it to the register beforehand. And I don't need to know what B is. That doesn't be the cost of the box. That's not changing. If I put in more snack mix, it costs more at this rate, $2.75 $2.75 per pound. And I don't have to put in whole pounds at a time. Any number of pounds times 2.75, fractional, weird decimal, or whatever it is, random scoop size, times 2.75 tells me the number of extra dollars I have to pay because of that scoop, just because of the change. So let's think about this. Now I'll start this off with, let's say that X, so we are not doing this backward from one another. Let's say X represents the number of pounds of snack mix that are in the gift. When you start, when you finish, it's something that's changing during this problem. See if you can come up with what might be the value for the meaning of Y, and what dx and dy and m would mean, or their values so far. And we'll talk about a specific problem. So this is just kind of a setup so far. Take a minute, see if you can figure out how to define what y is, and dx and dy, and m. Alright, so let's see. X in this situation is representing the number of pounds of snack mix in the gift. What would y need to be then in order for us to complete a relationship here? Some other quantity. What other quantity besides pounds of snack mix are we dealing with here? Cost. All right, so is y, let's see, it could be a total cost at the end, it could be a cost at any point in time while you're making it. Let's just call it cost. And the units for it, though, are going to be in dollars. So cost of the gift with X pounds of snack mix in it, or just the cost in dollars. But we need to make sure you have your units understood. When you're setting up a problem, make sure you define what units you're talking about, because it's really easy to, like, you've been thinking about it for a while, you have an idea of what units you're using in your head, and then someone else looks at us like, oh, is this X in minutes or is that hours? Like, oh, yeah, I meant hours. Make sure you clarify what units you're talking about when you're dealing with problems like this. So what if X and Y are these two? X is the number of pounds of mix in the gift. What would dx represent then, based on how we've been using this symbol? Yeah, a change in the number of pounds of snack mix. So dx being positive would maybe mean I take another scoop and put some more in. If I think about dx being negative, maybe I put too big a scoop in, I'm going to put some of that back when no one's looking. I don't want them to see me scooping this back out, especially if it's been mixed from multiple bins or whatever. But yeah, so dx would be changing the number of pounds. It would be talking about how much more or less the weight was, like changing the number of pounds of snack mix in the gift. So what would dy be about? What would that be representing? Yeah, the change in the price. So again, if you're increasing the number of pounds, you'd be increasing the price. If you're decreasing the number of pounds by scooping some back out, you'd be decreasing the price. But dx and dy are talking about those changes, or letting those vary, how changing one affects the other, well, is related by m. What's the value of m for this question? Yeah, it's at $2.75. The $2.75 per pound, it's that constant rate of change. It's the per pound charge of snack mix, however you want to describe this. So constant rate of change is the generic sort of term of y to x. But in this case, I can say, oh, it's the unit price of my snack mix, would be the, in context, normal way that people would say that. But this is a unit price, but that's a constant rate at which you pay based on, if you change one thing, you change your price. All right, so scooping some mix into a box, you decide you want some more. The additional cost you pay for 1.5 more pounds of, I guess called trail mix, snack mix, whatever it is 2.75 times $1.5. All right, so this is just a described situation here. Based on what we talked about, just defining these variables, these symbols that represent changing values. If this is the situation described up here, what's the value of dx that goes with this description? What's the number for dx? 1.5. Is it a positive or a negative 1.5? Positive. We increase the weight by 1.5 pounds. What about dy? You don't have to multiply it out, but it would be this, right? Also positive. It would be the change in the price. 1.5 extra pounds at $2.75 a pound costs me this much extra. This is the change in my price. M is still 2.75. It's a constant rate of change. All right, so we'll pick up with this next time. I'll see you on Thursday. Again, if you're having trouble with logging in to anything, let me know, let Zach know, contact somebody, and let's get this situated.
I do